Okay, section 3.3, digital inputs and outputs and pull resistors. This is a section from the Real-Time Computing for Mechanical Engineers book by me, Garbini, and Devine. MIT Press is the publisher. Check it out on their website or check out the companion website, rtcbook.org. Okay, starting us off with digital inputs and outputs. Before we can communicate digitally, we must be able to generate and detect digital signals. We will focus on single-board computers as the generator and detector of digital signals, but the principles also apply to many devices that generate and detect digital signals. Single-board computers for real-time computing commonly have several digital input-outputs, DIO, that each can be configured as either input or output. Sometimes these are called GPIOs, or general purpose input-outputs. Digital outputs. For a digital output, or DO, a digital signal, usually voltage, VO, is asserted to the associated pin as shown in the figure. So we have a single board computer and we have a voltage V out that is being asserted between the digital ground pin and the digital out pin. An output load would then be connected between those two pins. VO is always either high or low. The logic levels depend on the device, but they are often compatible with a 5, 3.3, or 2.4 volt CMOS logic family. Most single-board computers can source and sink a small amount of current to assert high and low levels at the output pin. Such DOs are called push-pull outputs, named for its transistor output stage. Other digital devices have open collector, bipolar junction transistor, or BJT, or open drain, metal oxide semiconductor field effect transistor, or MOSFET, outputs that can flow current in only one direction, typically to ground. We will consider these other output types further when we encounter more digital devices in Chapter 5. For now, though, we will focus on push-pull digital outs. Okay, the first of 4 input configurations: floating high Z input with a pull-down resistor and a connected input. Configured as a digital input, the input pin has high input impedance, called high Z, making it appear like a voltmeter to the circuit to which it connects. That is, it has minimal effects on the connected circuits that it is detecting and takes on the voltage VI of the connected circuit. So in this figure, we see the connected input. So we have some input voltage that is experiencing through this digital input a high impedance. The footnote notes the fact that this is sometimes called a third logic state, and DIs with this capability are sometimes said to have 3-state logic, which is not to be confused with 3-valued logic. So could be 1, 0, high, low, or high Z. When no input circuit is connected to the pin, or the input circuit is also in high Z mode, the pin's voltage is floating or indeterminate. This can be undesirable in certain cases, and therefore most DIs have an internal pull resistor, usually in the range from 1 to 40 kiloohms, which sets the default voltage of the pin. Some DIs will have an internal pull-down resistor, RD, that pulls the floating voltage down to the low logic level of the digital ground, D ground, pin, as in this figure. So in this case, we have an internal pull-down resistor that pulls this input to ground when there is no connected input asserting a value here to Di. Note that when the input circuit is connected, the pull-down resistor has little effect. So this is a high enough resistance that whatever is asserted here with a connected input overwhelms this default connection between the digital input and the digital ground. It's only when the connected input is disconnected that that pull resistor has a significant effect. When the output is disconnected, as shown in the figure, the pull-down resistor brings the input pin to ground. So now that we've disconnected the input, this digital input pin will approach the ground voltage. There will be a current that will flow here to make these in steady state the same voltage. This is the default state of the input pin when no external circuit is connected to it. So this is floating high Z input with a pull-down resistor, disconnected input, that case. Okay, so now let's have a pull-up resistor and connected input. So the pull-up resistor will make the default value of this digital input pin the high voltage, so connected to VCC, so it will go to high voltage when the connected input is disconnected. But when the connected input is connected, the fact that this default value is high will not have a significant effect on the connected input's value. However, when the input is disconnected, this digital in will float to or will be drawn toward the high voltage level. So the direction that the pull resistor is connected to gives the digital input a default value, either high or low. A little bit more on pull resistors. The resistance of a pull-up or pull-down resistor typically is not crucial because very little current should flow through it. If necessary for the application, it is possible to override the direction of the internal pull resistor by adding an external pull resistor in the opposite direction. However, the internal resistor remains, which results in a voltage divider circuit. So the external resistor must have sufficiently small resistance to pull the floating voltage to the proper level for the logic family. Too small of a resistance can overload the capacity of the digital supply or demand too much energy in battery-powered applications. So a calculation is necessary, and we do that in problem 3.2 at the end of the chapter. In some applications, the input circuit may itself be floating and require that we reduce the pull resistance from that of the internal pull resistor. This can be achieved with an external pull resistor in parallel with the internal one, as we explore in problem 3.3. Okay, so that's an introduction to digital outputs, digital inputs, and pull resistors. Pull up resistors, pull down resistors. Okay, I'll see you next time.